Hello everyone. We're going to start this video by talking about TCP Modbus, Serial Modbus, and the input capabilities that Mach 3 has, because I think you need a solid understanding of those prior to actually writing a brain which is going to use that kind of information. The real power of brains comes into full effect when you're dealing effectively with the data that's coming in. So let's just clear up a few misconceptions first about where the data is and how to do it. Here on the screen you can see I've got a little box and it represents Mach 3 itself. Now Mach 3 is typically speaking to a printer port, as we can see here. The printer port normally takes care of all of your inputs and outputs, and typically you don't need a whole lot of brains to deal with printer port inputs. Mach 3 already has a lot of logic built in for those types of inputs. That's not to say that brains aren't useful. You can obviously use a printer port input to or output to trigger events based on what Mach 3 is doing. But as I said, the true power comes in when we start to add Modbus. Now Mach 3 has over here two sets of buffers. There's an input and an output buffer, this light green and dark green area, which is Serial Modbus. Then of course you have the TCP Modbus, which is represented here by this blue and purplish buffers. These are buffers full of 16-bit words. There are 1,023 of them in TCP, and there's 128 of each in Serial. And they contain all of the data which is being sent in by a PLC on a repeated basis. The PLC is constantly sending data into the TCP input registers or into the serial input registers, depending on whether you're using serial or TCP. The PLC is constantly sending data into the input side of a mod from the TCP output registers, illustrated here in purple, back to the PLC. This is basically all a PLC does, is it's constantly sending data into Mach 3's appropriate buffer and constantly taking data out of Mach 3's buffer. The PLC oftentimes has a logic program that is operating on that data, determining what to do, whether or not to activate a valve, or various actions depending on the logic programmed in the PLC. Now if we take a look at one small section of TCP Modbus, we're going to discuss TCP Modbus primarily, but you can imagine that the PLC can also be sending to the Serial Modbus. The serial, as you can see, goes from address 0 to 127. There's an input buffer and an output buffer. Here in TCP, we have address 0 to 1023. So if we grab one address arbitrarily, let's call it address 981, and take a look at it in profile, we can see that there's an input register and there is an output register. Both of these registers are 16 bits wide. That is to say that you can have 16 bits of data in them, and they might be an analog value from 0 to 32,768 plus or minus, or they could just be a digital 1. Using brains, you can access any one of the bits, or you can use all 16 bits as a complete value, and that value is always an integer because PLCs only send back and forth 16-bit integers. There are ways to represent integers as doubles, but most PLC programmers will already know those methods. Typically, though, you're sending back and forth a 16-bit word. So when we're talking about TCP Modbus and Serial Modbus, that's really what you have to imagine, is that Mach 3 has an input buffer of 1,024 words, an output buffer of 1,024 words, a corollary of that in serial with only 127 input words and 127 output words. Actually, it's 128 words. We always start numbering at 0. And if you look at a particular address, like address 981, you could have an input address or an output address. And all you're really referring to is the buffer that the PLC is sending into, or the buffer that is sent out to the PLC. So we have an input side, which is Mach 3's, what Mach 3 sees as an input side, and we have an output side, which is what Mach 3 sees as an output side. Brains will deal primarily with that logic when you're dealing with a PLC. You want to take a look at data that's coming in from a PLC, manipulate it somehow using forms of logic, and then sending it back out to that PLC. Now, the logic that you have written for the PLC is important in terms of what the brain is doing with the data. The two actually work together to create a coordinated program. For example, Mach 3, when it sees a particular button being pushed or an input going active, may want to send a notification to the PLC that such has happened. So a brain, for example, could take a look at a DRO and say the XDRO has just gone above 10, therefore I will set one register or one bit inside this TCP output buffer, and that is what will be sent to the PLC. The PLC will then see that bit or register change to reflect the status of that DRO, and it will then use its own logic to deal with it, and if there's anything Mach 3 has to do, it will then send back a word into the input TCP buffer, which you can use a brain or a macro to deal with to perform whatever logic that you needed to perform in that context. Alright, now that we've looked at input buffers and output buffers and how they work, we'll look at writing a couple of TCP programs. I'm just going to pull up the brain editor here, and we'll call this TCP test, just for an example. And let's look at the real-life problem of a row-column switch matrix. I realize some won't know what that is, but some Modbus devices, as they're programmed, will send you two pieces of information on different addresses. One will be the row of a switch which has been pressed, and the other is a column of a switch that has been pressed. You could picture, for example, a 4x4 matrix of switches. The PLC will decode that to two words, row and column. So let's add those two words. We're going to go to the Modbus, and let's assume that address 100 is the row. We're just going to use serial Modbus, so we won't check TCP, and we're going to use the entire word, so we won't check the bit only. So here we have Modbus address 100 being used as an input. Let's also add another input and call it Modbus address 101. So for the sake of argument, we're going to say that the top row here, or the top input, is the row information coming from the PLC, and the bottom one is the column information coming from the PLC. So now let's look at what we'd have to do if we want that row and column to press a button for us. First thing we'll do is we'll click on the row and add a lobe and make it a comparative lobe. So we're going to say compare immediate equal to 0. With the column, we'll also compare immediate and say, is it equal to 0? And what we want to do is push a button if both the row and column are equal to 0. So we're going to select those two lobes and select an AND function. And what we're doing when we say that is we're saying if the previous lobe and the next previous lobe are both true, then we want to perform a function. So if we look at this as a functional program, we're saying Modbus address 100 if it's equal to 0, and Modbus 101, the column, if it's equal to 0, we want to do something. In this case, we want to push a Mach 3 button. So we're going to terminate that AND lobe with a button press. And we could make it any button, say the feed hold button. And there we have it. There's one switch out of the matrix. Now it may seem nasty to you, but in order to do the next switch in the matrix, you would have to repeat this process selecting different rows and columns. So for example, we would again add Modbus variable 100, and we would again add Modbus variable 101. Only this time, when we create our comparators for them, we're going to say compare immediate equal to 1 for the row, and we'll repeat equal to 0 for the column. We then, I messed up on that one. make sure you check the compare immediate button. If you just leave it on no operation, you're going to get exactly that, no operation. So we're going to say equal to 0 on this one. And then we're going to select those two lobes and add an AND lobe. And we can terminate that lobe with a button press, and basically any button in the system, so we'll call that single step. So there is two buttons on our switch matrix programmed. We have row and column of 0 and row and column of 1 and 0. And we could repeat this method for as many buttons as we'd like to input. On a 4x4 matrix, you could, of course, get 16 buttons. So you could repeat this 16 times to have your row and column matrix decoded. Again, brains run so fast that you needn't worry about how many inputs or how many lobes you're putting on your screen. It is best to try to do your logic one step at a time. Some people, because of the way they work, will try to first fill the left-hand side of the screen with 25 different variables they intend to use. And it's not a good idea, and let me show you why. If we add a couple inputs here, let's add address 103 in the Modbus, and let's add Modbus address 104, and maybe Modbus address 105. If you add all these inputs thinking, okay, now I'll use them, you may find that your assumptions in what order you put them in were wrong, and you'll end up, say, using these two inputs for a lobe. Let's call that an AND lobe. And now you'll notice that Modbus 104 is isolated. It's stuck in between two inputs. This will mess up the graphics of what you're trying to draw on your screen as a program, and it makes it very hard to coordinate it with other things. If we now add another input, we'll call it Modbus address 106, for example. If we now want to use 106 with 104, and we try to add a lobe, you can see that the lobe draws on top of the previous lobe. This is because Mach 3 is assuming a relationship from one input to the next, that they're used in the proper order. By misusing their order, you create a problem where you can't read what you're doing on the screen. It's very hard to tell what's going on. You can click on a lobe and hit minus, and it will delete the lobe that you just added. You can't always delete something in Mach 3. You'll notice that I can't even select these inputs here because Mach 3 is knowing that they're used, and you can see there's a screw up here where I can select 101. That doesn't mean I should. It just means something screwed up in my deletion, and the logic of the program now believes that input is available for use again. You can only typically delete things backwards, one level at a time. You can delete several inputs by selecting them, but you'll find at times an input may switch to unused and you won't be able to delete it. So my point here is that it's best to do your program one step at a time, thinking about what you want to do and making them in the right order. So that's a short example of a Modbus program which would decode a matrix and push a button. When a button gets pushed, it only gets pushed once. The inputs must change and then go active again before it would be pushed again. So for example, in this situation where we're doing a row and column compare of 0 and 0 to push the feed hold button, if those two Modbus addresses get set to 00, the feed hold will be pushed. If they change, the feed hold button will not get pushed again. It will only be pushed when it gets changed back to 0 and 0 on those two Modbus inputs. In other words, it's a high active triggering on the button push, and you don't need to worry about it getting reactivated. This brain, as we have it written, if row and column was indeed on Modbus address 100 and 101, this would work as a proper brain for the first two buttons of your matrix, and you could add as many buttons as you wished, up to the 16 maximum of that 4x4 matrix, and have it push the various buttons inside Mach 3. Okay, so that's how to do a more complex brain. Still not real complex, but as you can see, it's starting to build a little bit in complexity. Now, let's say that a person did not want any of these things to work, any of these outputs to work, when you're in eStop, because in eStop obviously you don't want to be pushing a bunch of buttons. So, and if we click on the lobe and hit terminate, it will say re-terminating lobe, and we say remove terminator. We then do the exact same thing, re-terminate the lobe by removing the terminator. Now we can add an input. In this case, let's look at one of Mach 3's outputs. In this case, we're going to use enable 1. Enable 1, all the enables actually, always is active only when the system is not in eStop. When you reset Mach 3, enable 1 will go true. So in this case, we're going to select, have enable 1 control whether or not this row and column 1 and 0 can actually put out its signal. And just by selecting those two and adding another AND gate, we've now just disabled that from putting out to whatever button we had selected. Let's make it a stop file button. So there's a more complex brain where we're decoding the matrix of the two Modbus incoming registers, row and column, 1 and 0. So, and then feeding it through an AND gate coupled with the enable 1. What this means is that the row and column matrix will not press the stop button unless the system is not in eStop. And this goes back to what I was saying about properly planning your brain. If you intend to put in that kind of a system, you may want to plan it in advance, because now there is no way for us to couple an enable 1 to the first switch. Although we can do it by cheating. If we now add another enable 1 input, enable 1 output, we can now tie that through the top one with an AND gate. But as you can see, the video gets quite screwed up. You now don't know exactly what you're ANDing. But it will allow us to terminate it to a button press of, say, cycle start. But it's now very hard for you to tell what exactly is activating cycle start. We know, since it was the last lobe added, that we're actually terminated on the proper output, but it looks like hell. So that enable 1 should have been just after the first two Modbus checks. So this goes back to how you're going to design your program. In this case, you would have to delete way back in order to get it back to the state that you can now add your enable 1 and continue on with your program. And as you can see, it's just a matter of point and clicking your way through, terminating to a button press, and there's our original feed hold button, done with a matrix comparison of row 0, column 0, and it's checking to make sure that it doesn't push the button unless the system is not in eStop. So you would repeat this 3 input sequence up to 16 times on this screen, and then save it as a matrix brain. So give some thought as to how to design a brain. If you're going to deal with multiple situations of inputs and so on, design one input first. It's a lot simpler for you afterwards to simply use that as the template for how you're going to design the rest of the switches. Now that I know I have one switch which is going to operate a feed hold, and only if the system is not flashing reset or in emergency stop situation, it's a lot easier for me to create 16 more copies of that using different switches and different row and column comparators to select the various switches that I wanted to do for this matrix switch program. So that's one more example of how to design a brain. More videos will follow as I add more selections for you. The program can now expect as inputs user LEDs. You use the exact same numbers as you would in Mach 3. OEM LED 1012 would be the 12th one. There are 255 OEM LEDs. You can also use OEM DROs to feed in. So you can trigger a brain by having an OEM LED. That means a button on the screen could set an LED, and the very fact that that LED was set is what will trigger the brain into operation. So those are the kinds of things that you can do at this point. More on that in the next video.